follow-up, we have Paolo from the University of Pavia, which is recently elected an Asian PhD student that works with Moni. And we talk about its research project. And it's about Morawetz, identities, and coercive formulation for wave equation.
Can I not use the microphone? Can you deliver me fine?
You have to turn it off.
Okay, so I'd like to present my research project for my starting PhD. It's on Morawetz identities. Maybe, I guess I left. It's on Morawetz identities and coercive formulation for the wave equation. Okay, so let's start from evolution PDEs, just very briefly. Of course, a simple approach to discretize and solve evolution PDEs is to discretizing one component, say time, and then solve the resulting problem, or another approach is just to discretize the space and then solve the ODE which results. In the recent years, though, many other numerical methods have been proposed exploiting space-time formulations, in that you do not, in a sense, discriminate between time and space. They're just variables. So the problem just becomes a glorified elliptic equation in a sense. For parabolic equation, this is actually a bit easier because there's a quite simple continuous and coercive formulation on the space-time cylinder, meaning the product of the space domain and the time domain. So many methods have been proposed, very diverse. So for a hyperbolic equation, instead, the situation is a bit trickier. We do not have such a formulation. It is not easily available, and so if one wants to discretize a hyperbolic equation in space-time, most of the time you just have to build your own discretization and prove that the discrete problem is actually well posed, and you need to prove convergence estimates. So it's a bit more challenging. So the simplest, of course, hyperbolic equation, it's just a wave equation that considers some random initial condition and boundary conditions. As I mentioned, there is no continuous and coercive formulation on the space-time cylinder. In literature, many strategies have been proposed. The most common one is just to use discontinuous hierarchy. If the objective is to find a continuous and coercive formulation, just so that we can use just simple Lux minimum. We can start by looking at the Helmholtz equation. Now, the Helmholtz equation in dimension 2 and 3 is actually quite. It is possible to construct a continuous and coercive formulation. If we start from this is just the usual sign indefinite formulation, just you multiply by a test function and we integrate by parts. If we use, instead of that identity, if we use this identity here, just the Morawetz identity, which one can prove is verified, and we integrate this and do some manipulation, we obtain that on a specific space with a specific norm, which you have to define, a k-dependent norm, just for the sake of explicit estimates of convergence errors. We obtain a bilinear form, which is this thing here, and a linear form. Well, the linear form is just easy because you put everything you do not want, you put it inside of the linear form. So it's easy. The bilinear form, well, you see there's these two terms here which are the same sign, which is fine. Also, this term here, it's also positive and consistent with the other signs. So where's the catch? Well, it's not magic. We are just moving the problem from the volume term into the boundary term. Although for the boundary term, there's a nice thing, because if we compute explicitly this mu times LV conjugate, this gives some boundary terms which, in a sense, cancels out the negativity of this term here. So, globally, the whole bilinear form turns out to be coercive. There's also a technical condition, which is that omega needs the domain needs to be starred with respect to a ball. That's just technical conditions. Another starting point is an article by Steinbach and Zank, who proposed a coercive formulation, a discrete coercive formulation, which is very specific. It works with piecewise linear functions in both space and time. This was the wave equation of the element. So the interesting thing in this article, I will talk about later, but it has to do with the fact that you can approximate approximate a function in a Lopian space in a specific manner. So, yeah. So the idea is to have a Lopian space and a bilinear form of such a Lopian space, also sort of linear form. And you have to define a specific norm in such a way that the bilinear form, of course, is coercive. Okay? It's very easy. The way we can do that is just as for the Helmholtz equation. So we have to find a Morawetz type identity on the space-time cylinder and use that to construct a bilinear form. And we have to prove also that the bilinear form is coercive, otherwise it's useless. Okay, I want to mention another kind of continuous formulation for a hyperbolic equation. This is very general. It's by Lyons and Magenes, but it's not the direction I'm interested in. This is, in a sense, seeing an hyperbolic equation as an ODE inside an inverse space. And it's not very interesting because, at least from a numerical point of view, it's not very interesting because it's just very similar to an in-soup formulation. It just gives a bound on the solution just on the datum, and so I mean it's just energy estimate. So not to the main appealing thing about the coercive formulation, I think, is just the quasi-optimality, which of course makes this worth the coercive formulation worth. So let's go to the wave equation. If we consider those two operators, of course, we can actually construct this identity, which is a Morawetz type identity. Because Morawetz identity is not like this, it's somewhat similar. The objective at this point becomes finding, now proving this is quite easy, but of course you need to find the right function alpha, beta, and z, which is the hyperpole, of course, because still you need them to be you need them in a way such that the bilinear form that you get is coercive. So I'm gonna skip on the space part because we still haven't found the space part, the coefficient for the space part of the identity. So yeah, there's that. But on the time component instead, you can use the argument I was mentioning before. So as did in the article by Steinbach and Zank, you just take you can prove that in a certain Bochner space you can approximate any function as a series of products, the eigenfunctions of the minus Laplacian, and an H2 function, which is somewhat reasonable. And if we take this approximation and we put it into the wave equation, and we drop the eigenfunctions, we drop the space component, one get the Helmholtz equation, the one-dimensional Helmholtz equation. Just it's a sort of a heuristic argument. It's not very formal, so just to give us some ideas on how the time component of the Morawetz identity might look like. So let's just consider the one-dimensional Helmholtz equation. The result that I showed earlier works in 2D and 3D. In one dimension, the problem is a bit different, mostly because this is an initial value problem. The one before was assumed to be a boundary value problem. So you need a different Morawetz identity with a shifting factor. And this shifting factor captures the fact that it is indeed the information on the domain is not spread around the boundary, but it's just all concentrated on one side of the domain. So still, with this, you have to take A, which is this A here, which is bigger than capital T, and you can find, if, for example, you pick it like capital T, we obtain a coercive formulation, a coercive linear form, with respect to this norm, which turns out to be equivalent to the usual H2 norm. So yeah, this is the coefficients, continuity coefficient and the coercivity coefficient, the quasi-optimality constant, which we were after. And just to test that this wasn't just a fluke, we did a very simple numerical test just to see if it was actually working or not. So since we are in H2 and we want to use conforming elements, that's the point of the formulation. Otherwise, well, we have to do computation. We have to. There's no point in using a non-conforming finite elements if we find the coercive formulation. It's my opinion, just more work. So we take those basis function. It's P3C1 continuity across the elements. These basis functions. The derivatives and co-derivatives, and well, yeah, it looks a bit weird, but we obtain optimal order of convergence until the step size is probably too small, but still, and then the errors start to grow back. Let me see the time effect. Okay. A probable explanation is, let's go back to this. In the formulation, those derivatives, the basis functions, I don't know if you can see it, well, the red one and the light blue one, they have 0, they assume value 0, and the first derivative is 1. So as you rescale from a reference element onto a small element of the mesh, this derivative grow, well, it becomes quite large. So you have, if you, in a sense, split the matrix, the stiffness matrix, into two parts, in the parts with the contribution from the green and blue functions and the one from the light blue and red functions, and you compute the condition number. The one for the first part, where for the green and blue function, the condition number is quite small. And all the conditioning comes out, for some reason, well, maybe that the reason that I mentioned earlier, from this light blue and red function. So, I don't know, maybe there is some scaling to be done, something, no idea still. So yeah, we also tested just for different values of k, just for the sake of it, fixed step size, and you get what you would expect. Of course, the error is large at the beginning because you are using too many elements to describe the solution. At some point, you reach an optimum, so you're using the right amount of elements to describe your function, and then the elements are becoming, you need more elements to describe the oscillatory nature of of the solution. So the arrows go back up. And so just concluding, the main objective is still, I repeat, is to find a coercive formulation for the wave equation. There are many ways one could do it. We chose to do it with Morawetz identity. Morawetz identity because it was similar to what has been done for the Helmholtz equation. So from the one-dimensional, the one-dimensional Helmholtz equation gives us the time component of the identity, whereas the space component of such an identity can be reasonably found using the same trick. So just some still a bit unclear. We might be getting that. So yeah, I conclude. Thank you.
Thank you, Paolo, for your presentation. And so, as usual, if there is any question, feel free to ask. Anyone? Okay, I'm coming.
Hi, Paolo. Thank you very much for your presentation. Very nice talk. And I wanted to ask you about that basis functions you're using. You're supposing that's the problem why you are narrow growth after a fixed step. Have you ever tried with different basis functions with maybe non-finite elements also?
Not really. I mean, we tried with this one because higher order methods are a bit of a pain, especially if you have to compute, if you have to impose one continuity. But it should be done. I mean, just for the sake of completeness, because yeah, it's likely that the problem is the basis function or maybe formulation.
It's okay? There is another question from the audience.
Thank you, Paolo, for the talk. Let me do a small trick. The fact that you're able to prove that there exists a coercive formulation to me implies something regarding the existence of a relational principle associated to your problem. And I was wondering if you could study things the other way around, like say try to devise a hard turning identity for a problem and maybe conclude that it's not possible to find the formulation under any kind of norms.
That's an interesting suggestion. I think so. A variational by variational principle, you mean something like finding the minimum. Yeah. We could do that, but let me just go back to. Okay. Let me just. I just take the Helmholtz equation just as an example, maybe. Yeah. So if you to a variational principle, you need the bilinear form to be symmetric, right? And this is sadly not. So.
Do you want to respond? Okay. So, any other question? Is there anyone suggesting that we should thank you once again?